y square, y into y. Y square is nothing but 5. In coefficient of y square is 5, so 5 is written here. Next, xz is 2zx. So dividing by 2 will be 1. So in this xz, 1 is there. Here also zx, here we are substituting 1. And yz minus 2 is there. Dividing by 2 will get minus 1, minus 1. Z square 3, z 3 will be in the same form. So all the diagonal elements will be of the square term, x square, y square and z square. We have to write all the values exactly, and all the non-diagonal entries we have to divide by 2 and we have to write. So this is a 3 by 3 matrix. That is the quadratic form is of 3 variables. So this will be a 3 by 3 matrix. If it is a 4 variables, we will get a 4 by 4 matrix. So we have to find the matrix of transformation. Matrix of transformation is nothing but this matrix. So this is how we reduce the quadratic form 3x square plus 5y square minus 3z square. Sorry, plus 3z square minus 2yz plus 2zx minus 2xy into this matrix, this canonical form. So nature of quadratic forms. So this is very important topic. We have seen in the previous classes in types of matrices that if under eigenvalues, if lambda is if it is a positive definite matrix, we know that lambda is greater than 0. So here nature of quadratic form. If a quadratic form, that is x transpose ax, this is the quadratic form. If the matrix A is if we can say this is positive definite if all the eigenvalues of A are positive, that is x transpose Ax is greater than 0 implies all the eigenvalues of lambda I of A is greater than 0. Then we can say that this quadratic form is positive definite, and it is negative definite if all the eigenvalues are negative. It is positive semi-definite if all the eigenvalues are non-negative. That is, positive semi-definite means it is greater than or equal to 0. Negative semi-definite means if all the eigenvalues are less than or equal to 0. Indefinite, that is, if some of the eigenvalues are positive and some of the eigenvalues are negative, then we can say that the matrix or quadratic form to be an indefinite one. Important results. Here, a necessary and sufficient condition for a real quadratic form x transpose Ax to be positive definite is leading principal minors of A are all positive, and for negative definite is that leading principal minors are of alternating negative and positive signs. It is nothing but, let us assume this as a 3 by 3 matrix. 1, 2, 1, 0, 1, 1, minus 2, minus 1, 0. Let us assume this is a matrix A. So positive, principal minus of A, that is, this is 1 by 1 minor. So D1, let us assume the minor of 1 by 1 as D1. Here D1 is equal, excuse me, that is the principal minor, D1 is, it is of 1 by 1 nature. Here D1 is equal to 1, 1 is greater than 0, then it will be a positive definite, and a positive definite one. If D2, considering D2, determinant of D2 is nothing but 1 minus 0, it is also greater than 0, and 3 by 3. Finding the determinant of this 3 by 3 matrix will be minus 1 into minus 1 into 0 minus minus 1 will be plus 1, minus 2 into 2 plus 1 into 0 minus of minus 2 is plus 2. So 3 minus 4, which is minus 1. So D3, determinant of D3 minor is negative. So it is not a positive definite matrix. If all D1, D2 and D3 are positive, then we can say that it is a positive definite matrix. And if for alternating, if D1 is positive, D2 is negative, D3 is positive and D4 is negative, we can say that it is a negative definite form, negative definite quadratic form. We can see examples later. Two quadratic forms are equivalent over C if they are of same size and rank. So a quadratic form X transpose AX is equal to X transpose BX if it is A and B are that is the quadratic forms are of same size and rank. Two quadratic forms are equivalent over R if they are of same size, rank and signature. Signature is nothing but number of positive eigenvalues minus number of negative eigenvalues. So we'll see sums for this. So in this, we have given quadratic form. We have to find the matrix 6x square plus y square plus z square plus 2xy plus 2yz plus 4xz. So in the coefficient of x square is 6. So for 1 by 1 is 6. 1 by 1 matrix is 6. Let us assume this row as x, this column as x, this row as y, this column as y, this row as z, this column as z. So x square 6x square. So x square is in the x square place 1 position we are substituting it as 6, and y square in y square place coefficient is 1, in z square coefficient is 1. In other forms we have to divide by 2. Xy, there are two xy positions. So 2xy 2 by 2 is 1. So it will be 1 here and 1 here. And yz is this 1 by 3 and 3 by 1 position. So dividing by 2 we'll get sorry, is 2 by 3 and 3 by 2. Dividing by 2 we'll get 1 and 1. So for x is 1 by 3 and 2 by 3. 4 divided by 2 is 2. So it will be 2 here and it will be 2 here. Another example, 6x square minus y square minus 4z square plus 3xy plus 4yz plus 2xz. X square 6, y square is minus 1, z square is minus 4. Xy is 3, so 3 by 2 will be here. And yz is this positions 4 by 2 is 2 and here 4 by 2 is 2. And xz coefficient is 2, so 1 and 1. As we can see, all these quadratic forms are of symmetric nature. This will be a symmetric matrix. So this will be a symmetric matrix. So next 4x square minus 3y square plus 2z square plus 4xy. So in the coefficient of x square is 4. Coefficient of y square is minus 3. Coefficient of z square is 2. And 4xy. So dividing by 2, it will be 2. So xy position 2 and 2. And other positions 0 is there. So we are substituting as 0 and 0. So this is the corresponding canonical form. That and the matrix of transformation. So signature is nothing but number of positive eigenvalues minus number of negative eigenvalues. So this is one important result. So we can say two non-singular Hermitian, or it also holds for real symmetric matrices. Two non-singular Hermitian matrices are congruent if and only if they have same signature. So if two Hermitian matrices have same signature, we can say it is congruent also. So in the same case, it is for real symmetric matrices. So we have to determine if A and B are congruent, that is A is equal to 1 0 0 minus 1. This is a symmetric matrix, and also it is a Hermitian matrix, real symmetric matrix. B is nothing but 0 I minus I 0. Here this is a Hermitian matrix because B transpose equal B bar is equal to B. That is a conjugate of B is nothing but B matrix itself. Conjugate transpose of B is nothing but B matrix itself. So these two matrices are Hermitian. So we can say that if they both have same signature, we can say that A and B are congruent. So determinant of A is -1. So lambda, finding the characteristic equation, lambda square minus trace. Trace is 0 here. 1 minus 1 is 0. Plus determinant of A. Determinant is -1. So lambda square is equal to 1. So lambda is equal to plus or minus 1. So lambda, this matrix has 1 and -1 as its eigenvalues. So positive number of eigenvalues is 1, negative number of eigenvalues is 1. So it's subtraction. One number of positive eigenvalues minus number of negative eigenvalues will become the signature of A. Signature is nothing but 0. 1 minus 1, 0. Finding the characteristic equation of the matrix B, lambda square, trace is 0 minus trace plus determinant of B. Determinant of B is nothing but -1, lambda square -1, same thing, same eigenvalues we are getting. So signature of B is nothing but 1 minus 1, which is equal to 0. Then we can say that A and B are congruent matrices. Next, we have to find whether this matrix A is positive definite or not. So in order to say a matrix is positive definite, we have to find the eigenvalues lambda 1, lambda 2 and lambda 3, since this is a 3 by 3 matrix. If all the lambda i's, that is if all the eigenvalues are positive, we can say it is a positive definite matrix. In other terms, in the result, what we have seen is all the minus, principal minus of the matrix A, if all the minus are greater than 0, then we can say that the matrix is positive definite. So D1 is nothing but 1. Determinant of 1 is greater than 0. First condition satisfied. And it, D2 is 1, 2, 2, 6. So it will be 6 minus 4 is 2. It is greater than 0. Or in other words, 2, any minor, 2 minus 0, it will be greater than 0. Any 2 minor is greater than 0. And D3 is the determinant of the whole matrix, which is equal to 3. It is also greater than 0. Hence, we can say that if D1, D2, and D3 are greater than 0, hence A is positive definite. Another sum here, A is a 4 by 4 matrix. We have to see whether it is positive definite or not. Here D1 is positive. All the D1s are positive. And D2, we can see this D2. Here 1 minus 4 is -3, which is less than 0. Here D2 is negative. Hence, A is not positive definite. It doesn't mean that A is negative definite, but they are asked to find whether it is positive definite or not. Then we can say it is not positive definite. Next question. F of xy is equal to x square minus 4xy plus 5y square on R2. So we have to convert this into canonical form. So we'll get the matrix x square is 1, y square is 5, minus 4xy is dividing by 2, we'll get -2 and -2. Here D1 is greater than 0, that is 1 and 5 are greater than 0. D2 is nothing but the whole determinant of the matrix. So 5 minus 4 is 1, which is also greater than 0. Hence, we can say that A is a positive definite matrix. And also, we know that any quadratic form can be written in the canonical form, where this matrix is always symmetric. We can see that it is always symmetric. All the non-diagonal, except the non-diagonal elements, it will be symmetric only. It will be same only. So hence we can say that F is both symmetric and positive definite. So option A is correct. Next we have to find which of the following matrices are positive definite. Here D1 is greater than 0, 2, 1, 4 are greater than 0, and D2 minus 2 minus 4 is not greater than 0, hence this is not positive definite. Here, here in this D2 minus 12 minus 1, it is not positive. It is less than 0, hence it is not positive. Here D1 is greater than 0 and all the D2s are greater than 0, and D3, if you check D3, all D3s will be greater than 0, and the determinant of this matrix is also greater than 0. Hence this is positive definite matrix. You can also find the eigenvalues and we can say that whether it is positive definite or not. Next, one more sum. A is a 3 by 3 matrix with eigenvalues -1, 1, and 2. Find alpha, beta, gamma so that A inverse is equal to alpha A square plus beta A plus gamma I. So, here eigenvalues are given and we have to find the A inverse in the matrix form of A. So, first of all, let us find the characteristic equation. So we know that let us assume the eigenvalues lambda 1, lambda 2, lambda 3 as -1, 1, 2. Trace is nothing but sum of the eigenvalues, which is nothing but 1 minus 1 plus 2 is 2. And determinant of A, determinant is product of these eigenvalues, which is nothing but -2. So in characteristic equation for 3 by 3 matrix, lambda cube minus, we can write as trace of A into lambda square plus summation of lambda I, lambda j into lambda minus determinant of A. So this is the characteristic equation for any 3 by 3 matrix. Here we have to find the summation of lambda I, lambda j. For that, lambda 1 into lambda 2 is -1, lambda 2 into lambda 3 is 2, lambda 3 into lambda 1 is -2. So by adding all this, we will get -1. So lambda cube minus trace is 2. So minus trace of A is 2 lambda square and summation of lambda lambda j is -1. So minus lambda minus determinant of A. Determinant of A is already -2, hence +2 is equal to 0. By Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. So here the matrix A satisfies this equation. So we are substituting lambda, we are substituting A instead of lambda. So A cube minus 2A square minus A plus 2I is equal to 0. By taking the matrix A outside, we'll get A square minus 2A minus I is equal to, taking this 2I to the right hand side, will be minus 2I. So take multiplying with A inverse, that is taking this A this side, and by making this -2 dividing by -2, we'll get A inverse is equal to -1 by 2 A square plus 2 by 2 A plus 1 by 2 into I. So A inverse can be written as alpha A square plus beta A plus gamma I. So this is alpha. Alpha is -1 by 2. Beta is 1 and gamma is 1 by 2. So this is the values of alpha, beta and gamma. Next topic, bilinear and Hermitian form. So what is a bilinear form? Let V be a vector space. Let V be a vector space over a finite dimension over a field K. Then the bilinear form of on V is a mapping from f of V cross V to K. So V cross V to the field K. So such that for all AB in K, for all scalars AB in K, and for all U and V vectors in vector space V, these two conditions holds in bilinear. Whether in the case of this second condition, f of u comma av1 plus bv2 is nothing but a into f of uv1 plus b into f of uv2. In the case of inner products, in the second condition will get conjugate. If you have seen yesterday's class, and for inner product, u comma v distributive property, if scalar is multiplied in the second space, while taking out, it will be a conjugate of this conjugate of the scalar. Here it will be like this only. We express condition 1 by saying f is linear in the first variable and condition 2 by saying f is linear in the second variable. So if these two conditions are satisfied, two linear conditions are satisfied, hence this is known as bilinear form. So let f be the dot product on R power n. Here f of u comma v is nothing but u dot v, that is a1 b1 plus a2 b2 plus an bn. where u is equal to all a's, b equal to all b's. Then f is bilinear form in r power n. So dot product on r power n is the bilinear form. And gba dot product on c power n. Let us assume g of u comma b is u is all zi's and v is all wi's. Z1 W1 bar plus Z2 W2 bar plus Zn W1 bar. Then the complex dot product is linear in the first position. However, in the second position, we are not taking the conjugates. So we are not taking the k bar outside. We are taking only the k outside. Hence, it is not linear. Then on C power n, it is not a bilinear form. So as I said, here in the second position, only the real part comes out. So it does not hold for complex C power n. Let pi and sigma be arbitrary linear functions on V. Let f from V cross V to k be defined by f of u comma v is equal to pi of u into sigma of v. Then f is a bilinear form since pi and sigma are linear functions. They have already given pi and sigma are linear. Hence, the bilinear form is also a linear in both cases. Hence, f is a bilinear form. For example, f be a bilinear form on R power 2, defined by f of x1, x2, comma y1, y2, given by 2x1, y1 minus 3x1, y2 plus 4x2, y2. So we have to find the matrix A with respect to the basis 1 comma u is equal to 1 comma 0 and u2 is equal to 1 comma 1. So let us take here a11 if for a matrix means we have position A11, A12, A21, A22. So A11 is nothing but f of u1 comma u1. That is Aij is nothing but f of ui comma uj. So A11 is f of u1 comma u1. That is f of 1 comma 0 comma 1 comma 0. Here x1 into y1. X1 into y1. This is x1, x2, y1, y2. x1 into y1 is 1. Uh, 2 into 1 is 2. And x1, y2. x1 and y2 is 0. So 0. x2, y2 is also 0, 0. Thus a11 is nothing but 2. Similarly, finding all three values. A12 is substituting this in this defined f. We'll get A11, A12, A21 and A22. Thus, we obtain the matrix A. Next, polynomial bilinear form. A polynomial f of xi comma yi in variables x1 to xn and variables y1 to yn is called bilinear polynomial if f of xi comma yi is equal to summation I equal to 1 to j, summation j equal to 1 to n, aij xi yj. That is a11 x1 y1, a12 x1 y2, a1n x1 yn. Similarly, a21 x2 y1 and up to ann xn yn. We can write this in matrix form. That is a11 and a12. We will get a12 x1 y2 and a21 x2 y1. So we will get a matrix and it is pre and post multiplied by these vectors x1, x2, xn and post multiplied the column vector y1 to yn. Or we can say f of x comma y is nothing but x transpose ay. X transpose is the row vector, y transpose is again the row vector y1 to y1 and a is nothing but this matrix. So if we can write like this, then we can say that it is a polynomial bilinear form. That u is equal to x1, x2, x3, v is equal to y1, y2, y3. That f of u comma b be written like this. Please note that this is not the this is actually similar to the quadratic form, but this is actually bilinear form. Here A is a 3 by 3 matrix whose ijth entry is the coefficient of xi, yj. Here x1, y1 is 3, x1, y2 is minus 2, Similarly, x2, y1. x2, y1 is 5. Here the matrix is not symmetric. This is not a quadratic form. Here it is. This is called the bilinear form, polynomial bilinear form. This is different from the quadratic form. If in quadratic form, the matrix will always be a symmetric one. So, and x2, y2 is 7, x2, y3 is -8, x3, y2 is +4, x3, y1 is -1, and remaining two positions 0 and 0. This is the matrix form. So, we have to determine whether all these examples are bilinear form or not. So, let us assume f of u comma v is equal to 2x1 y2 minus 3x2 y1. So, we can write this as um, x1 y2 as 2, x2 y1 as -3, remaining position 0 and 0. So this is a bilinear form. And the second one, x1 y2. Here the terms are not it is not of degree 2, that is it is not product of x and y. So if it is a product of x and y, we can write it as a bilinear, that is we can write it as a matrix notation. Hence they are not of the form, the terms are not of the form aij xi yj. So it is not a bilinear form. First one is a bilinear form. Second one, 3x2 y2, it is a bilinear form. It can be written as 0 0 0 3. And fourth one, x1 x2 y1 y2, it is not the product of x and y, hence it is not a bilinear form. Here, fifth one, x1 y1 plus 2x2 y2 plus 3. Here, this constant term is not a form of not a product of x and y. Hence, this is also not a bilinear form. U comma v is equal to 0. It is a bilinear form. Since the matrix null matrix 0 0 0 0 is a bilinear, we can write like this. So it is a bilinear form. F of u comma v is equal to 1 is not a bilinear form because we cannot write in a matrix form. So 1, 3, and 6 are the bilinear form, and all the other things will not come under bilinear forms. So these are some of the results. Here let V be any vector space over K. Let F be the zero function. And as in the example, we can say that f of u comma v is equal to 0 is bilinear. If f and g are bilinear, then some f plus g is bilinear, and scalar multiplication is also a bilinear. Let B of V denote the collection of all bilinear forms. Then B of V form, it is a vector space with respect to vector addition, scalar multiplication. Then the collection of all bilinear forms is again a vector space itself. Let V be a vector space of dimension n. Then phi 1 be the basis. Phi 1, phi 2, phi n be the basis of V. Then we can say that Fi's, that is, it is a Fi's are defined by phi I into phi j, phi I into phi j, F1, F phi j. F phi j is nothing but phi I into phi j. So here all the Fij is the basis of B of V. B of V is nothing but the collection of all bilinear forms. Thus, dimension of B of V is nothing but n square. Here we have pi 1, pi 2. We can express it in the form of pi 1 1, pi 1 2, pi 1 3. So we will get n square terms in the basis. So dimension of B of V is n square. Rank of a bilinear form. The rank of a bilinear form is written as rank of F is defined to be the rank of any matrix representation. So this is the matrix representation of 1. So if we find the rank of this matrix, we will get the rank of the bilinear form of f of uv defined as in 1. So rank of a bilinear form is nothing but the rank of the corresponding matrix representation. A bilinear form is said to be degenerate if rank of f is less than dimension of v. It is said to be non-degenerate if rank of f is equal to dimension of v. Next, Hermitian forms. In Hermitian form, It is similar to bilinear form except the condition. It is over VBA vector space over the complex field C. And Hermitian form, first and second condition. First and second condition is same as first 1 and 3, where the scalars are the conjugates. Where the scalars are the conjugates. And we know that f of u comma v is equal to f of v comma u the whole bar, the conjugate of this. If all these three conditions are satisfied, we can say that f is a Hermitian quadratic form or complex quadratic form. The rank and signature of Hermitian form are denoted and defined by rank is equal to p plus n. P is nothing but positive number of eigenvalues. N is negative number. Negative entries in the diagonal representation. That is negative. We can write this in the diagonal form. Your signature is p minus n. P is the positive entries, n is the negative entries. It is not eigenvalues here. So in this Hermitian form, we will get diagonal entries. The diagonal entries, we all know that it is nothing but eigenvalues. So signature is p minus n. P is the number of positive entries, n is the number of negative entries. Your rank is nothing but p plus n. So a Hermitian form f is said to be positive definite if f of v comma v is greater than 0, and we can say it is non-negative positive, non-negative semi-definite if f of v comma v is greater than or equal to 0 for every v. These are some of the exercises we have to show. We have to see whether which of the following matrices are positive definite. Here 2 is positive definite. 2 into 2 is 4 minus 1. This is a positive definite matrix. 1 is positive definite and determinant of D2 minor is 1 minus 4. This is not a positive definite matrix. 4 is a positive definite matrix. 4, so 16 minus 1. 16 minus D2 minor determinant of this matrix is positive. Hence, this is positive definite. D1 is equal to 0. It is not greater than 0. Hence, this is not positive definite. It might be positive positive semi-definite or negative semi-definite or negative or indefinite. But in this case, we have to check whether it is positive or not. It is not greater than 0. Hence, this is not positive definite. So, A and C are positive definite matrices. Here, suppose A is a 3 by 3 matrix defined like this, which is equal to xy minus 1. Let P be the number of positive eigenvalues. Q is equal to rank of A minus P. Then we have to find the value of P. So we have to find the matrix A. So matrix A is nothing but x into y. This is Z column is nothing but a constant column. X into y is 1 comma 2 position. So 1 by 2. Here it is 0. This is again 1 by 2. 0. 1 into x term is not that. That is, this form does not contain x term alone. So 0. And this does not contain y term alone. 0. And this is 1 position. That is the constant position. Constant is minus 1. Minus 1. We have to find whether we have to find the eigenvalues of the matrix. Then only we can find P and Q values. Here, rank of the matrix is rank of the matrix is this is a symmetric matrix. Yeah, P is the positive eigenvalues. Q is the number of. They didn't give the value of Q, so we have to find the eigenvalues. Eigenvalues will be lambda. Minus lambda 1 by 2 0 1 by 2 minus lambda minus 1 minus lambda. Taking this minus lambda into 1 plus lambda minus 0 minus 1 by 2 into Taking minus outside, we'll get again 1 by 2, that is 1 by 4 into 1 plus lambda. Taking 1 plus lambda outside, we'll get minus lambda square plus 1 by 4. So lambda is equal to minus 1 and lambda square is equal to 1 by 4. So lambda is equal to plus or minus 1 by 2. So number of negative eigenvalues is 2. Number of positive eigenvalues is 1. So P is equal to 1 also true. Q is equal to 2 is also true. And that's all for today. So the important topics are eigenvalues, eigenvectors and vector spaces and subspaces and determinants and algebra of matrices. And there will be questions on these quadratic forms also. So these are some of the topics. Practice some questions and you will be good.